Hello dear students, welcome you all. In this lecture I am going to discuss about the M-ary modulation technique, right? This is the next digital modulation technique that I am going to discuss in this lecture, right? Earlier we have discussed about the amplitude shift keying, right? That was also known as binary amplitude shift keying, then BFSK, binary frequency shift keying, then BPSK, that is binary phase shift keying, and then differential phase shift keying. All these techniques I have discussed in the earlier lectures. Now I am going to discuss this M-ary modulation technique here. So in M-ary modulation technique, M stands for multi-level, right? Level. Right. So in M-ary modulation, we are going to use multi-levels of either amplitude, frequency or phase, right, to represent the information, right. So this is the main thing that make it different from binary kind of shift keying techniques. We know very well in binary shift keying techniques, whether it is BASK, BFSK, BPSK or DPSK, we were only using two levels for representing the information. We were using only 2 bits, 0 and 1, right? So we can say 1 bit per sample, right? So that's why it was called as a binary shift keying technique. But now we are going to use more than 1 bit, right? So it can be 2 bits, it can be 3 bits, it can be 4 bits, depending upon the requirements. So why it is required? The question arises, why we are going for a multi-level shift keying techniques. So for that we have to recall the bandwidth requirement for all these shift keying techniques. We have seen that in all these cases the bandwidth requirement is approximately, I can say, it is 2 times the baseband frequency, right? Or I can say the bandwidth requirement is high, right? So in order to reduce the bandwidth requirement and send more information in small bandwidth, this technique is used, M-ary modulation technique. Now you can see here in this diagram here, I am showing a binary shift keying technique and also M-ary shift keying technique, right? So in binary you can see that there are 2 levels, either 0 or a 1. This is 1, this is a 0. So the information signal, message signal, that is encoded in this format, right? And I can say if the time period of the cycle is 1 second, then in 1 second time I have 1, 2, 3, 4, 5, 6, 7, 8 samples, right? You can see here bit rate is equal to 8 bit per second. In 1 second I have 8 bits or 8 samples. Now if in place of 1 bit I use 2 bits, right? You can see here, right? 1 1 1 0 0 1 0 1 0 0 0 0 0 0 1 0. So all these are different levels, you can see here. So now instead of using 2 levels, I am now using 4 levels. This is 1, 2, 3 and 4, right? These are 0 0 are the lowest levels, right? Then I have a level 2 is what? It is 0 1. I know very well that the binary clock advances in this way: 0 0 0 1 1 0 1 1. So 0 0 is 0, it is 1, it is 2 and it is a 3. This is the lowest level. So you can see here, then 0 1 is the next, then next will be the 1 0. You can see here it is 1 0, this one and this one, and then 1 1. So you can see here the information that is represented, it is represented by 8 into 2, 16 bits, 16 samples, right? So in 1 second I can take 16 samples. So this method is more convenient. We are sending more information per unit time, right? Bit rate is high as compared to this. So this is the advantage, right? This comparison clearly demonstrate that in this second technique, M-ary technique, I am capable of sending more information per unit time, right? And obviously the required bandwidth will be low, right, for the given number of given amount of data, right? In general, we takes when m in M-ary, m is equal to 2 raised to power n, where n is the number of bits used, right, and m is the number of levels, right? That is also called a symbol, right? Sometimes it is also written as a symbol in shift keying techniques. So if I take n is equal to 1, then in this case n is equal to 1 means 1 bit per sample, either 0 or 1, right? Then in case I will have only 2 raised to power 1 means 2, m means 2, m is equal to 2. So this was the technique that is shown here, right? You can see only 1 bit per sample. But if I take n is equal to 2, right, then m is equal to 4, right? You can see here, right? So here we are taking a 2 bits per sample, right? Similarly, if I take n is equal to 3, then what will become 2 raised to power 3, 8. So m is equal to 8, right? Similarly, I can increase the number of samples in the given time. So this is the main difference between binary ASK, FSK, PSK and M-ary shift keying technique. Now I am coming to the all M-ary modulation techniques one by one. I mean, it can be M-ary ASK, it can be M-ary FSK, it can be M-ary PSK, right? So all these three techniques will be discussed one by one in this lecture, right? So first of all, I am coming to the M-ary amplitude shift keying modulation technique. You can see here. Now, as I told you that in binary phase shift keying, binary amplitude shift keying BASK, I was using only 2 levels of the amplitude, either 0 or 1. 0 corresponds to different amplitude, 1 corresponds to different amplitude. You can see here in this figure, BSK 2 level, 1 bit for a 1 symbol, right? You can see 0 and 1, then 0, then 1, then 0, then 1, right? So this is data density is 1 bit, right? 1 bit per sample. But here you can see now I am using 4 levels of the amplitude, right? As I told you, here it is 0 0, then 0 1. You can see this is 0 1, then I think it is again 0 1, then it is 1 0, right? Then 1 1. So you can see here in this diagram that there are 4 different amplitude values of the modulated ASK signal, right? The information is contained in high frequency carrier wave in 4 different amplitude levels, right, which are encoded as per the binary format, right? 0 0, 0 1, 1 0 and 1 1. So this is the difference. I told you in the early lectures also that in binary we are using only 2 levels, but in M-ary we are using multiple levels depending upon the requirement. So you can see here the difference in this diagram. Now in actual, we know very well that I can represent a M-ary modulated wave as AI into cos of omega c t, right, where t is taken for the time period that is for 1 cycle, right? T greater than 0 equal to 0 to less than equal to Ts, 1 complete cycle, and AI is given as 2I minus 1 minus m, right? So here I can and I goes from 1 to m, I mean 1 2 3 so on, whatever the value of m we are taking, right? So I can see here it is d also, sorry I forgot to write it here. So this is the value of AI, stands for amplitude. So we are using this formula. Now let's consider that we are taking m is equal to 4. This case m is equal to 4 and d is equal to 1, right? So d is equal to 1, d stands for the difference between the adjacent samples, right? So in this case, I can put all d is equal to 1 means now I am left with the 2i minus 1 minus 4. So if I put I is equal to 1, 2 minus 1, 1, 1 minus 4, minus 3. Then 2 2s are 4, 4 minus 1, 3, 3 minus 4, minus 1. Similarly, the next will be plus 1 and plus 3. So these are the 4 different amplitude levels, right? For the, this high frequency carrier wave, right? So now I can represent these 4 different waves as B1 is equal to cos of vega ct, and V2 is equal to minus cos of vega ct, then V3 is equal to 3 cos of vega ct, and V4 is equal to minus 3 cos of vega ct, right? These are the 4 levels, amplitude levels of this wave, right? Here I told you that we are taking difference 1 in terms of binary counting, 0 0 0 1 1 0 1 1. This is the meaning of it. It doesn't mean these will have a difference of 1, right? Because it is a separate thing, right? We are taking the digit binary counting into consideration, right? So this is about the M-ary ASK, amplitude shift keying. So in place of m is equal to 4, I can take whatever value I want to. Even I can take 3 bits, right? I can take 4 bits, right? For n is equal to 4, I will have 16, right? If I take n is equal to 4, then m will become 16. 16 different levels will be there. If I take n is equal to 3, then 8 different levels will be there. So this is different levels of the M-ary modulation in amplitude shift keying, right? Now I am coming to the next one. The next one is M-ary frequency shift keying modulation technique, right? Now recall that simple BFSK. We have learned about it. What was it? We know in binary frequency shift keying, we were using only 2 values of the frequency. One corresponds to 0 and one corresponds to 1, right? Only 2 levels were there. But now here I can change whatever value I want. If I take n is equal to 1, then m is equal to 2. That is that is this binary. But if n is equal to 2, then m is equal to 4. 2 examples are shown here. This is binary, amplitude frequency shift keying. Here you can see you have 1 corresponds to frequency, corresponding frequency is this, 0 corresponding frequency is this, 1 1 corresponding frequency high, 0 corresponding frequency low, right? So 1 bit per sample, right? But here we are taking 2 bit per sample, right? You can see, so 0 0 different frequency, 0 1 different frequency, 1 0 different frequency, 1 1 different frequency. So we are using 4 different frequency values here, right? In M-ary FSK modulation technique, but in simple binary phase shift keying, we were using frequency shift keying, we were using only 2 different frequency levels, right? So as far as the formula for taking the frequency is concerned, so again I know that Vc is equal to A. In this case, amplitude is fixed, cos of 2 pi Fci t, right? With the condition that we are taking interval t goes from equal to greater than equal to 0 and less than equal to ts, right? And I goes from right. Now let's consider the special case when if I take m is equal to 1, right? Then in this case it will become a cos of 2 pi fc t, right? If I take this is v1. Similarly, b2 a cos of 4 pi fc t if m is equal to I is equal to 2, right? So this is the way, if I take I is equal to 2, then in this case, sorry, I forgot to write down the formula for FCI here. So FCI is equal to FC, right, plus I minus M divided by 2 into delta F. This is the formula, right? This was actually wrong. I write it wrongly, so sorry for it. So actually here you are given this relation for the modulated frequency shift keying waveform, high frequency carrier wave, and here FCI. So FCI is given as FC, central frequency, carrier frequency, plus the deviation, right? That depend upon I and M, right? So you can take the value of M. If I told you M is equal to 4, then you can take different values of I. 1, 2, 3 and 4. So according to that, you will have different frequencies as they are shown here, right? For example, if you take I is equal to 1, then what will be there? It will become fc plus I is equal to 1 minus 2 minus 1. So it will become minus 1 into delta f. So it will become fc minus delta f. Similarly, if you take I is equal to 2, then 2 minus 2, then because it is 4 by 2, so 2 minus 2, it is 0. So it is equal to FC, right? Similarly, if you take I is equal to 3, so 3 minus 2, 1, then it will become FC plus delta F. So this is the way of finding the different frequencies by using this relation that is taken into this equation, right? So this is M-ary FSK modulation, frequency shift keying modulation, right? Now I am coming to the next one, that is M-ary phase shift keying modulation. Now we know very well that in BPSK, right, and even in DPSK, differential phase shift keying, we are using only two phase angles, right? One for 0 and one for 1, right? But in this M-ary PSK modulation, we are going to use multiple levels depending upon the number of bits used, and the formula is M is equal to 2 raised to power n. If n is equal to 1, M is equal to 2. That is shown here. If M is equal to n is equal to 2, M is equal to 4, right? So this is shown here. You can see here. So in again this M-ary phase shift keying modulation, we are going to use multiple levels of the phase angles for the high frequency carrier wave instead of taking only two angles, right? You can see here that the simple this is the simple BPSK. Here 1 corresponds to this. When we take 0, then there is a change of 180 degree in the phase. But when we take 1, there is no change in the phase remains the same, whatever it was going from here. Then again, when it is 0, the phase is changed 180 degree. So two values of the phase angles 0 and 180 degree were used. 0 corresponds to 1 and 180 degree corresponds to bit 0. But when I am using 2 bits per sample, right, you can see 2 bits for one sample, 0 1 1 0 1 0 1 1 and 0 0. Now in that case I am using different angles for 1 0 and 0 1, totally different. You can say 90 degree, 180 degree, 180 degree, 270 degree and 0 degree. Now how these angles can be calculated? So for it again I am going to write down the expression that was very well, V M-ary is equal to A cos of 2 pi omega c t plus phi I, right? Phi I again, the rule is I goes from 1 to m, and t is taken greater than equal to 0, less than equal to ts, and the formula for calculating phi I is equal to 2 pi upon m into I minus 1 plus a constant. Now two situations arise, right? One situation is that in which constant is taken as 0, right? Constant is taken as 0, then I can take different values of I. For I is equal to 1, the angles will be phi I is equal to 0, pi by 2, pi, and 3 pi by 2. You can see here, this is 0, already constant is taken as 0. So I is equal to 1, 1 minus 1, 0. I is equal to 2, 2 minus 1, 1. So m is equal to 4. We have taken m is equal to 4 also. M is equal to 4. So when m is equal to 4, 2 by 4, we are left with pi by 2. So pi by 2 into 2 minus 1, 1, pi by 2. So pi by 2 into 3 minus 1, 2 means pi. Pi by 2 into 4 minus 1, 3 pi by 2. So these are the different phase angles that are going to be induced, right? You can see here, right? This is the case of this particular example. This diagram is for this particular example. Now we can have another kind of this M-ary PSK modulation, where this constant is taken as a pi by 2, right? If constant is taken as pi by 2 and m is taken as 4, then in that case, again same thing, but you will get pi by 2 added to. So you will get pi by 2. No, it is I think pi by 4. Pi by 4, not pi by 2. Constant is equal to pi by 4. So when 0 plus pi by 4, pi by 4, pi by 2 plus pi by 4, you will have a pi by 2 plus pi by 4, 3 pi by 4, right? Similarly, the next will be 5 pi by 4, and the next will be 7 pi by 4. So these are the different phase angles when I take constant is equal to pi by 4 and m is equal to 4. So this type of modulation is called pi by 4 M-ary phase shift keying, right? Phase shift keying, and this is simply called as M-ary phase shift keying when constant is taken as 0. So these are the different M-ary modulation techniques that can be utilized to decrease the requirement of the bandwidth, to increase the power efficiency, increase the bit rate, increase the amount of data sent per unit time. So all these things can be improved by utilizing the M-ary modulation, right? So in the coming lecture, I will discuss these M-ary, simple M-ary PSK modulation, and M-ary pi by 4 PSK modulation in detail, right? So thank you very much.